In the instruction fetch stage, the CPU behaves like a librarian who knows which book, instruction to pick next. The program counter PC holds the address of the next instruction, just as a card catalog number points to a book location. The CPU copies the address from PC to the address bus. The memory responds with the instruction word, and the instruction register (IR) latches it. Immediately after the fetch, the PC is updated. PC becomes PC plus 1 for byte addressable machines, or PC becomes PC plus instruction length for variable length sets. This increment prepares the PC for the following fetch, ensuring sequential execution unless a branch changes the PC later. During instruction decode, the CPU examines the bits of the fetched instruction to figure out what action to take, similar to reading the title of a recipe to know which ingredients are needed. The opcode field, often the high order bits, is extracted. Opcode becomes IR31:26 for a 32-bit RISC instruction. A decoder translates this binary pattern into a set of control signals, for example reg DSD, a LUSRC, mem-read, mem-write branch. These signals steer later stages. They decide which registers to read, which a LU operation to perform, and whether memory will be accessed. The decoding logic can be thought of as a lookup table that maps each opcode to a unique control word. Operand fetch is the stage where the CPU gathers the data that the operation will work on, much like gathering vegetables before cooking. The decoded control signals tell the register file which registers to read. Read reg 1 gets IR25:21, read reg 2 gets IR20:16 for a typical R-type format. The values are placed on the internal data bus and loaded into temporary registers A and B. If the instruction uses memory addressing, an effective address is computed, EA equals base plus index times scale plus offset. For example, in a load word instruction, EA equals R base plus sign extend offset. This calculation is often done by the ALU in a pre-X step, preparing the exact memory location for the next stage. Execution is where the arithmetic logic unit, a LU, performs the actual computation, analogous to a kitchen mixer blending ingredients. The ALU receives its two operands from the A and B registers, or an immediate value if ALU source equals 1, and performs the operation indicated by the ALU control signal, for example add, sub, and or SLT. The result is result equals operand 1 operation operand 2. After the operation, status flags are updated. 0 equals result equal to 0, negative equals result less than 0, carry equals unsigned overflow, overflow equals signed overflow. These flags are later used for conditional branch decisions. The ALU may also produce the effective address for memory operations, so the same hardware can be reused for arithmetic and address calculations. In the memory access stage, the processor interacts with the external memory hierarchy similar to a mail carrier delivering or picking up a package. If the instruction is a load, the address calculated in EX is placed on the address bus, and a read cycle is initiated. The bus cycle timing typically follows a fixed number of clock periods. Address phase 1 cycle, data transfer phase 1 to 2 cycles depending on memory speed. The data returned from memory is stored in a temporary register MDR. For a store, the data to be written from register B is placed on the data bus while the address is driven by the ALU, and a write command is asserted. Timing diagrams show the address and control lines being stable during the address phase, and the data lines becoming valid during the data phase. Write back is the final step where the result of a computation is stored back into the register file, much like putting a finished dish back on the serving table. If the instruction is an arithmetic operation, the ALU result is written into the destination register. Reg write reg becomes result. For a load, the data fetched from memory MDR is written. Reg write reg becomes MDR. The control signals reg write and mem to reg determine which source, a LU or memory, supplies the data and which register receives it. This completes the instruction, making the new value visible to subsequent instructions. Register Transfer Language RTL provides a concise math-like way to describe the micro-operations that occur in each stage. IR becomes M of PC, PC becomes PC plus 1. A becomes reg of read reg 1, B becomes reg of read reg 2, result becomes a plus B, reg of write reg becomes result. The left side denotes the destination register or latch, the right side denotes the source expression, and the arrow indicates that the transfer happens on the active clock edge. RTL abstracts away physical wiring, but captures exactly what data moves where and when, making it useful for design verification and teaching. Micro-operation timing defines when each RTL statement happens relative to the processor clock. In a classic non-pipeline CPU, each instruction occupies 5 clock cycles, 1 per stage, IFIDOFEXMEMWB sometimes folded. Each micro-operation is assigned to a specific cycle. For example, cycle 1 IR gets M of PC. Cycle 2 opcode gets IR of 31 to 26. Cycle 3 A gets reg of read reg 1. Cycle 4 result gets a op B. Cycle 5 reg of write reg gets result. In a pipeline design, these cycles overlap. While instruction I is in EX instruction, I plus 1 can be in OF, and instruction I plus 2 can be in ID, etc. This overlapping improves throughput, but introduces hazards. Data control structural. Pipeline registers, pipeline latches hold the intermediate results between stages, and control logic stalls. Forwarding ensures correct sequencing. The timing diagram of a 5-stage pipeline shows a diagonal flow of micro-operations across clock cycles, illustrating the concept of parallelism in modern CPUs.